Everyone, sorry I can't be in class with you today, but you've got a great guest teacher with you, and I'm going to go over today's lesson in this video. So it'll be as if I'm actually there, and then there'll be times where you pause the video and you guys will work in groups, and then unpause the video and I'll debrief the activity with you. All right, so first I want to let you know that your standard 5 tests are graded. I was going to return it to you today, but since I'm not there, I'll return it to you next class. We're going to do retakes for that test on February 5th, so just kind of keep that date on your radar. And then our current unit, Unit 6, that test will be on February 7th. So speaking of Unit 6, if we go back and kind of look at the overview of this course, Unit 6 is about similarity. Okay? Similarity is a concept kind of like congruence, but not exactly the same thing. All right, so if you haven't already done so, make sure that you put your phones in the front of the room. We can pause the video here to give you time to do that, and then once we're done, go ahead and have a seat, and then we'll take a look at our learning target. All right, so what are we going to learn today? So we're going to figure out what it means to dilate a figure. Okay, now the word dilate you might have heard in your everyday language. If you've gone to have an eye exam recently, usually they'll put some drops in your eye that will dilate your pupils. That makes it easier for them to take measurements. So dilate means to enlarge something. Okay. All right, so here are the 4 things that we're going to learn in this activity. Number 1, how to find the scale factor of a dilation, how to tell whether a dilation is reducing an image or enlarging an image. Okay. Graphing dilated images using coordinates, so x and y coordinates, ordered pairs, and then using scale factors to solve real-life problems. All right, so on our agenda, we'll skip returning the test. I'll do that next class. We'll probably skip the which one doesn't belong. Again, we can do that next class. Let's just go straight into our activity. So your guest teacher should have a handout for you, and that handout has an image of LeBron James and a bunch of questions about that image. So if you need to pause the video here to pass out the papers, go ahead. When you're ready, you can unpause the video. Okay, so here's the activity, and then here's kind of the inspiration for the activity. So you guys have all heard of LeBron James. He's probably the most famous basketball player. And he currently plays for the Lakers, although he's played for many other teams. I think he's won 4 championships. He no longer ranks 3rd on the all-time scoring list. He's now 1st place. So he's scored more points than any other player who's ever played in the NBA. Okay. So you can find posters of him like everywhere. You know, go to Target or Walmart or Amazon, and I'm sure you can find a poster about him. But you know, does a poster really do him justice? Like, do you really get the sense of like how tall of a human being he is just from looking at a poster? Okay. All right. So this is a 3-page activity. You've got page 1, page 2, and the last page is our quick notes. Now there's a stop sign before you get to question 9, so obviously we're going to pause and debrief there. Okay, so right now what we're going to do is work for about 15 minutes on questions 1 through 8. Okay. All right, I'm going to roll a die. Oh, here, you guys can watch me do it, so it's fair. And we'll decide who's the reader for today. Let's see, roll die. Okay, let's roll a 4-sided die. 2. All right, so if you're in seat number 2, you're today's reader. All right, so a couple things that you might need is when you get to question 5, okay, your guest teacher will tell you what LeBron's true height is, but we're not going to reveal that yet because we want you to make a couple guesses first in question number 2. Okay, so someone in your group can raise their hand when you get to question 5, and then your guest teacher will come and tell you what value to use for question number 5. Also, another thing I want to highlight here is make sure that you're measuring in centimeters. Okay? And if you haven't already gotten some tools, you're going to need a ruler and a protractor. So you're going to be measuring lengths and angles. Okay, let's see, is there anything else I need to mention? No, I think that's good. All right, so pause the video here, and then in 15 minutes, you can show the guest teacher how to set the timer. So in 15 minutes, unpause the video and I'll debrief questions 1 through 8. All right, so you've worked for 15 minutes, and so now let's go ahead and compare answers, and then also have a red pen handy because I'm going to add some additional notes and introduce some vocabulary as we do this debrief. Okay. All right, so I kind of imagine what a student might say if they were doing this activity. Obviously, I couldn't take photos of your work. So things that you might notice about this photo, number 1, he's tall. It's kind of assumed because he's a basketball player. Secondly, you can tell which team he plays for. He's wearing the jersey. Some things you might wonder. So even though he's tall and plays in the NBA, how tall is he compared to other NBA players? And then maybe you're wondering, what is that white sleeve on his arm? What function does it have? So it doesn't really have to be mathematical questions that you had, but just kind of anything that you were thinking. All right, question number 2. We're making 3 guesses for how tall he actually is. So 6 feet would probably be too low. Okay, so 6 feet. There's probably some 6-foot tall players in the NBA, but usually you got to be much taller than 6 feet to play in the NBA. All right, 7 feet. That's obviously too high of a guess. The tallest players of all time are like 7 feet tall. So, your Shaquille O'Neals, your Victor Wembanyama's, those are 7-foot people, right? They're like the tallest human beings, not just basketball players. Okay, so a reasonable guess for LeBron's height might be, 6 feet and 5 inches. Okay, now your guess might be a little different. It's okay, you don't have to change your answer, but this is a reasonable guess. All right, now question 3. Now everybody took different measurements, and I'm not sure whether you rounded or not. So the values that I have here might not exactly match what you have on your paper, and that's okay. But as long as they're reasonably close, right, we'll call that a win. Okay. So if you measured his height in this picture with your ruler, hopefully you got something around 12.5 centimeters, right? Maybe you rounded down to 12 or up to 13, that's fine. Okay. The length of the word Lakers on his jersey, right? So we're talking about this right here. That should measure in at around 1.5 centimeters. Okay. His head, so how tall his head is there, that's also about 1.5 centimeters. So those two measurements should be about the same. Okay. Right. His leg length would be 7.5. So I think that's that distance right there. His torso, so that would be this distance right here, coming in at about 3.5 centimeters. And then the angle made by his right elbow. Now, when I do this in class, students always ask, well, is it his right elbow or, from our perspective, the right elbow? So I went ahead and measured his right elbow. That's the one with the sleeve. So this angle right here, okay, was a little less than 90 degrees. It was about 80 degrees. Okay. All right, so if your numbers aren't too far off, that's fine. Don't change them. But if you got numbers that were really off from these, go ahead and update it to the measurements I have here. All right, let's move on to question number 4. So question number 4 wants us to find a ratio. Okay. Now a ratio is simply a comparison of two numbers, and the way that you've compared numbers before in the past is by making a fraction, right? One number is the numerator and another number is the denominator. Okay. So we're going to look at the torso to leg ratio, or the torso to leg fraction. Okay. So 3.5 was the measurement I got for his torso. Again, yours might be a little different. 7.5 was the measurement I got for his leg. Using a calculator, dividing one measurement by the other gives me a decimal version of this ratio, 0.47. Okay. Now you might not get exactly 0.47, and that's okay, but hopefully you got something somewhat close to 0.47, maybe like 0.4, 0.5, somewhere in that range. All right, so what does this number mean, 0.47? Okay. Well, you can think of it as being really close to 0.5 or 0.50, which in the world of percents, that would be 50%, which we know is exactly half. Okay? So this number is telling us that his torso is about half, a little bit less than half, the length of his leg. All right, question number 5. Okay? Let's think about real life LeBron. Okay, so when this photo was taken, he was 6 feet 9 inches tall, or because we took all our other measurements in centimeters, that would be equivalent to 206 centimeters. Okay. Let's figure out how many times bigger real LeBron is versus photo LeBron. Okay. So again, we can use a ratio, right? We're looking at his real life measurement in centimeters versus his photo measurement in the same units, centimeters. Okay. Dividing one measurement by another gives this value 16.48, okay, which is close to 16.5. Right. So we can conclude that the real LeBron is 16.5 times bigger than what you see here in this photo. All right, now here's where I want you to grab that red pen. Okay. So the two numbers in this fraction, right, the top number is his real life measurement, and the bottom number is his photo measurement. Okay. So in words, the ratio is real measurement versus photo measurement, or real measurement over photo measurement. Okay. And we're going to call this ratio, or this fraction, the scale factor. Okay. So to scale something means to enlarge it or to shrink it. Okay. In this case, we are enlarging the photo measurements by a factor of 16.5. All right, question number 6. Okay. Now, the idea here was to use your scale factor, which hopefully was something around 16.5. Might have been a little bit smaller, a little bit larger, depending on what you had for the photo measurement. So to use that to figure out what all the other real life measurements are. Okay. So to figure out how long the Lakers wording is on the jersey, the idea would be to take the photo measurement, multiply it by 16.48. Okay. So I'll write it here in red. What did I have? 1.5. So this would have been, on the calculator, 1.5 times 16.48. Okay. The way I got the size of his head was to do the same thing, right? Take the measurement that I got from the photo, so I got 1.5, yours might have been something different, and then multiplied it by that scale factor, 16.48. All right. For his leg, I had, what did I have? 7.5. So this would have been 7.5 times 16.48. The torso, that would have been 3.5 times 16.48. Okay. And then the last one, the angle of his elbow. We don't need to multiply that one, okay, because that's an angle measurement, which behaves differently than a length. Okay, so angle measurements actually stay the same. Okay, when you scale an image. Okay, so let's make a note here. Angle measures stay the same. Right, and that should make intuitive sense. If I had a triangle and I enlarged it, that triangle's angles would still add up to 180, right? It wouldn't now, add up to some bigger number just because it's a bigger triangle. All right. Okay, let me try to illustrate what I mean. Okay, so if I had this triangle, which I know the angles add up to 180, and then let's say I scaled it up. Okay. What happened to it? Okay, let's try that again. Oh, there, it's over there. Okay, so this other triangle, its magic number is still 180. Just because it's bigger doesn't mean its angles all of a sudden got bigger. Okay, so that was the point I was trying to make. All right, flip over to the second page and we'll talk about questions 7 and 8. All right, 7, how do the measurements on the photo compare to his real life measurements? Well, we know that his real life measurements are all going to be about 16.5 times bigger than what we got in the photo, except for the angle, right? So that part is important, okay? The angle stayed the same. Okay. All right, here's another opportunity where I want you to take some notes in your red pen. Okay. So the sides, or the lengths, get scaled by our factor. Sides slash lengths get scaled by a factor, okay? But the angles stay the same. So the angles don't change. Okay. So when we have two images, right, where we can see that the sides have been scaled by some factor, but the angles have stayed the same, we call those two images similar images or similar figures. All right, so sides are changing, right, by the same factor, and the angles stay the same. All right, so just like I had tried earlier, let me see if I can do it again. I'm just going to draw, a random. Here, let's draw a shape that you've probably all seen before. Right, that S, right? So I can take this shape and then I can resize it, right? So all the sides of this shape got longer, right, by the same factor. I don't know if it's double or triple or whatever, okay, but they all got longer by the same factor. The angles stayed the same, okay? So this angle here at the top is the same angle right there. Okay, question number 8. What is LeBron's real life torso to leg ratio? Okay, so we actually have to go back to question 6 to get those real life measurements. Okay, so the real life torso, I got around 57 centimeters, a little bit longer than 57, and the real life leg was 123 centimeters, excuse me. Okay. Now remember, those are my measurements. Yours might vary just a little bit. Okay. But when I set up a ratio with those two numbers, okay, and then I use a calculator to convert that ratio to a decimal, I get the same one that I got before, right? 0.47 was the exact same ratio that I got when I was using the photo measurements of his torso and leg. Okay, so it doesn't matter whether I'm using the real measurements of his torso and leg or the photo measurements of his torso and leg, I'm getting the same ratio. Okay. All right, so here's the big takeaway. Okay, the ratios of sides stay consistent after we enlarge or shrink an image. Right. So we kind of argued that his torso was about 50%, half of his leg ratio. It should be the same no matter what photo we're looking at or whether we're looking at him in real life. If all of a sudden his torso was no longer half of his leg measurement, then he wouldn't be proportional anymore, because those are his proportions, right? Half. All right, so we've gone up to question number 8. Next, what you're going to do is go back to working with your groups, and then you're going to do questions 9 through 12. Okay, let me see if I need to provide you with any information. Okay, so for when you get to question number 10, there should be another handout that your guest teacher will give you. So raise your hand when you're ready to do question 10, and your guest teacher will give you that handout. Okay. Yeah, okay, I think that's all I needed to say. So pause the video here, and then let's see, how much time should we work? Let's work for about another 15 minutes. Okay, so somebody can set the timer and then unpause this video in 15 minutes. All right, so you've finished questions, 9 through 12? So let's go ahead and talk about them. Okay, so question 9 wasn't really meant to be much of a mathematical question, but thinking in real life, how would you like resize a photo if you wanted to put it on different objects? So you can use like an online service that does it for you, or you can use some kind of photo editing software where you can just upload the image and then like drag a corner to make it bigger, right? Just like what you see me do here on the screen, right? If I have, say, an image of LeBron James, right, I can grab a corner, right, and drag it out to enlarge or push it in to shrink it, right? So kind of doing something like that. All right, question number 10. Look at the set of resized photos that your teacher handed out to you. So I think there were like 5 different images of LeBron. Which ones do you think were accurate? All right, so the accurate ones were the first photo, the second photo, and the fourth photo. Okay. Now you can kind of tell by just imagining somebody doing like what I did there, dragging the corner of the image in or out to basically resize it. Okay. All right, which is completely different than, here, I wonder if I could do this. I don't even know if I have PowerPoint. I don't have PowerPoint here. Never mind then. It's gonna show you like what happens when you drag the side of an image versus dragging the corner of an image. It behaves differently. All right, so the images that are accurate, those are called dilations. So I want you to write this word, use a red pen here by question number 10. Okay, so the first, second, and fourth images are dilations. And so a dilation is simply the sides are staying proportional or in the same ratio. Sides stay proportional, meaning they have the same ratio. Right. So one ratio that we've kind of already looked at a couple times before is the torso to leg ratio, right? So if you look at the torso to leg ratio in the first, second, or fourth photo, it should be the same as what you have in the original photo, which was about 0.47. All right. Here, this image might help you think about it as well, right? So when you have an image, what you can do is click and drag a corner, right? And that will resize the image. What you'll notice is usually the opposite corner doesn't move, it stays the same. And then it's just the corner that you clicked on, that one moves. Okay. So the other corner actually has a special name. It's called the center of dilation, right? Because that point never moves, we call it the center. Center of dilation. All right, question 11. Choose an image that you thought was accurate, prove it. Choose an image you thought wasn't accurate, and prove it. All right, so I chose to look at picture number 1. Okay, and what I did is I just looked at the length of the word Lakers on the jersey and the length of his head. And if it was the same measurement, which it was, right, then I knew it was accurate because in the original photo, those two measurements were the same. Here, I got 1.5 centimeters for both of those measurements in the original photo. And in picture number 1, those two things had the same measurement. Yeah. Now, picture 3, when I measured the word Lakers and his head, they were not the same measurement. In fact, the word Lakers had a much bigger measurement, which told me that the photo got wider more than it got taller. Okay, so it was stretched in the horizontal position. In the horizontal direction. All right. Our last question, number 12, is kind of a challenge question because we haven't really talked much about percentages. I think I might have mentioned it very briefly, here when I said 0.47 was close to 0.50, which would be 50%. Okay. So here we have a percentage. We want to scale something up by 350%. Okay. So we need to think about what that would be as a scale factor. Okay. So 350% would be equivalent to a scale factor of 3.5. Okay, so all our measurements are going to get 3.5 times bigger. Okay. All right, so we got to go back to page number 1. I'm going to use the measurements I had. So the original height I had was 12.5. Okay, I multiplied that by the scale factor 3.5. Okay. For the Lakers script, originally I had 1.5 centimeters, and I'm going to multiply that by the scale factor 3.5. Same thing for his head. Okay, 1.5 was the original measurement, and 3.5 is the scale factor. All right, for the leg, I had 7.5 centimeters originally, and then on the calculator just multiplied by 3.5. Torso was 3.5, multiplied that by 3.5. So there's two 3.5s there. Okay, the first 3.5 represents the original measurement I took, and the other 3.5 represents the scale factor, or this increase of 350%. Okay. All right, the angle. All right, remember that's not going to change. Okay, the angle stays the same when you dilate or enlarge an image. And then the ratio. Well, the ratio is going to be the same. If I take the torso to leg, right, if I take this and divide it by that, right, I get the same ratio that I got every other time I looked at the torso and the leg. It's this 0.47 ratio. So those two things stay the same. Angles and ratios stay the same, but all the other length measurements will change, get multiplied by your scale factor. Okay. All right, so we're done with the group portion of the activity. Let's do a quick summary. So turn to the last page, and we're going to write a couple things here in the quick notes. All right, so number 1, let's define the term similar figures. So similar figures have the same overall shape, but different size. Now notice that that's kind of, it should remind you of the definition of congruent, right? Congruent figures have the same shape and the same size. Okay, similar figures only have the same shape as one another, and they have different sizes, right? There's small versions, medium versions, large versions, but all of the same shape. All right, so that's the first note. The second note is this idea of a scale factor. Okay? So when we enlarge or reduce an image, we have to use the same scale factor to do it. So all the side lengths are enlarged or reduced by some scale factor. Now, we're going to use the abbreviation SF when we talk about a scale factor, and you can find it by just making a ratio of two measurements. You need to get a measurement from the new shape and divide it by the corresponding measurement of the original shape. So it's new divided by original. All right, couple final notes here is that the ratio of sides within and between the two figures are the same, stay the same. The ratio of sides within and between figures stay the same. So again, just think back to that torso to leg ratio, right? Whether we were looking at the original photo of LeBron or his real life measurements or some of those other photos of him on the second handout, that torso to leg ratio was always the same decimal. Okay. All right, so ratios stay the same, and then also the angles. Let me draw that a little bit better. So the angles stay the same when you dilate a figure. All right, so the big thing here is scale factor, right? Which is just a ratio, just a fraction of some new measurement divided by the corresponding original measurement. All right, you can pause the video here and just kind of keep the quick notes up on the projector screen. And then anybody who's still copying can go ahead and finish that. Once everybody in your group has copied the quick notes, then let's just maybe work for 5 minutes to do as many of the check your understanding questions as you can. So there are, I think, three questions there, right? So one about the dimensions of a room, another one about what looks like a hexagon shape, and then the last question is about a regular Coke can versus a mini Coke can. Yeah. All right, so go ahead and set 5 minutes on the timer. Let me go back and put the quick notes back here. All right, and then you can pause the video and then unpause it when you're ready to check answers for the check your understanding. All right, so you've worked for about 5 minutes, and maybe you did one question or two questions. That's okay. But let me go ahead and share the answers with you, and whichever questions you did work on, just check your answers. All right, so question number one. One of the big things here is that some of the measurements are in feet, and then, so these are the real life measurements, and then the blueprint measurements are in inches. Those are two different units, okay? So to get an accurate scale factor, we should use the same units. Okay? So I use the fact that 1 foot is equivalent to 12 inches. So 10 feet becomes 120 inches, and 12 feet becomes 144 inches. Okay? So the actual room is 120 inches by 144 inches. All right, now to find the scale factor, what I decided to do was take one of the real measurements and divide it by the blueprint measurement. Okay. So I did 120 inches divided by 7.5. I also did 144 inches divided by 9. Okay? They give me the same ratio, okay? Which is 16. So this tells us that the actual dimensions of the room are 16 times bigger than what's shown in the blueprint. All right, question number 2. So we have kind of this small hexagon and this large hexagon, and there's a couple missing measurements, and we want to figure out what those are. Okay. So to figure out some of the missing measurements, we first have to figure out the scale factor between these two hexagons. What I did is I found a pair of corresponding sides where I had both measurements. Okay. So I took I'm thinking of this as my new shape, and this is my original shape. And so I did one measurement divided by the other, and I got 1.5. Okay. All right, that's a nice clean number. So that's telling me that all the lengths here are 1.5 times bigger than in the small hexagon. Okay. So I can take any of these numbers here, multiply by 1.5 to get the numbers over here. And I realized that I missed one. I didn't figure out this one. So I'll just do it on the spot. So we're going to take 4.3. We're going to multiply that by 1.5 to get the new measurement. Okay. Did not have my calculator ready. So 4.3 times 1.5 is 6.45. Okay. Now, if you want to go the other way, right, if you want to take one of the measurements from the large shape and shrink it down for the small shape, you just have to unmultiply or divide by 1.5. Okay, so multiply by the scale factor to get bigger, divide by the scale factor to get smaller. Okay. So we did that here. We took this large measurement, we divided by the scale factor to get the small measurement. Okay. Now the one instance where you shouldn't multiply and shouldn't divide is with the angle. Okay, so that angle right there is going to be the same whether we're talking about the big or the small shape. It's going to be 124 degrees no matter what. All right, question 3, this is the last one about the Coke can. So we've got the regular can over here and the mini can there. We have both the height and the diameter of the regular can. We only know the diameter of the small can, the mini can. We want to figure out its height. Okay. So if you figured out both methods, awesome. If you figured out one method, that's still awesome. Okay. Here's one way of doing it. Okay. Find the scale factor. Okay. You'd have to use the corresponding measurements. So the only pair of corresponding measurements we have is the diameter. Okay. Now I want to go from big to small. So I'm thinking of this as my new figure and this as the original. Okay. So I'm doing new divided by original, or 0.64. Okay. Notice how that scale factor is a decimal. Okay. So when I multiply by this scale factor, my result is going to be a smaller number than what I started with. All right, so we're going to take this measurement here, multiply by the scale factor to get the corresponding measurement in the mini can. Here's the calculation right there. You get almost 8 centimeters. Okay. Right, a second method, which probably isn't as common, is to look at the height to diameter ratio. Okay. So if I look at the original can and just the original can, I want to ask myself, how many times taller is it versus wide? Right? And if you just want to do quick math, you can see that's about 12 and that's about 6, meaning it's about 2 times taller than it is wide. Okay. Now, if you use the whole numbers with the decimals and everything, okay, you get 1.96, which is pretty close to 2. Okay. So I can use 1.96, or if you just want to round to 2, I mean, that works as well. Okay. And so we'll take the measurement from the mini can, multiply by that factor of 2 to figure out how tall it is. It's almost 8 centimeters tall. Makes sense. 4 times 2 is 8. All right. So I hope this went okay for you. I know it's not ideal to try to teach you through a video, but hopefully you got something out of this lesson. I'm not sure how much time is left in the period, but if you've got time, go ahead and grab a laptop out of the cart, and then you can log into Big Ideas or log into Canvas and do some of your independent assignments, which would be you've got a reading quiz in Canvas and like 8 to 10 problems in Big Ideas. All right, so this video is going to end. I'll see you guys all next class.